Hello, everyone. Good morning. My name is Inan Musmulas. I'm chairing this session. As I said yesterday in the other networking-related session we had, I think this is I consider this as part 2 of the networking sessions, network management sessions. Today we're talking about applications. Yesterday it was about standardization and tools. So we have 4 presentations, a bit packed this day. We have 2 innovative applications building on top of Juno Space, the Juno Space platform. And there's also an interesting presentation about investigating network performance issues, and the presentation for the brand new, shining, integrated NMS for Jan. So first up is Radoslav Kritsvania for the first Juno Space related presentation.
Is this thing working? Can you hear me?
Okay. You can use your headset or...
Okay, it's working. Cool. Okay, so welcome those who are able to wake up today. So my presentation will not have so many fireworks, eagles, and crossbow shooting like yesterday, but I hope it still will be interesting. My name is Radek Krzywania. I'm working in the Poznan Supercomputing Center for quite a long time. What I want to present here is how we develop the NSI agents for Juniper boxes using the Juno Space environment, the Juno Space SDK. Most of the implementation work was done by Michał, who is mentioned here. So if you have a really real detailed question on that, he will be rather better person to contact than me. I just have an overview of that. Okay, so first thing is what is the NSI? So for those who are not familiar with the protocol itself, I'll say a few words on how this thing is working, what is the concept behind it. So the problem is that you have several domains managed by different people, different entrants, if you want to take a look at this in that way. Different vendors, completely independent, so you have all Juniper boxes, you have Brocade boxes, whatever. And then the network management system, who is helping you to manage the environment and set up the services within those networks. The problem is that this NMS or managers cannot talk to each other because there are different implementations and they operate in different environment. So for example, you have here the Autobahn, which is managing the Jan domain. You have DRAC, which is used, for example, by SurfNet. You have Japanese system, Glambda, US Oscars, Nordinet is in OpenNSA. Now, we want to make them collaborating together. So we need to have another layer, another tool that will enable communication between all those tools. So they can exchange information like topology, for example, availability of the resources, authorization, authentication stuff, of course, etc. So what we have done is to introduce the additional NSI interface, which is providing this functionality to all those tools. So you just add another block to your NMS, and this block allows you to talk to your neighbors. And your neighbors can also deliver the services to you. So what is the advantage of that? Is that you can set up your circuit here in one domain and go through all those domains till the end, because all those tools can communicate and can give you the services you want. The NSI work is done under the OGF, which is Open Grid Forum. You probably know it quite well. This is the links that leads you to the web pages when you can find more information in NSI. And if you're interested in the NSI itself, you may also join the working group. It's open for everyone. The features of the NSI are as follows. I would just go briefly through that list. The most important things is that we are now focused on the connection service, which in fact is delivering the circuits connections to the end user. So this is the end-to-end or rather edge-to-edge connection, because there's always last mile problem. We do that in advance. It means that you can request the circuit in a time from now, a week, a month, a year, and the resources are booked there and are waiting for you. And when you need them at the reservation start time, they are configured and delivered to you. So this is kind of a guaranteed service. There is, of course, mechanisms for authentication of the agents itself. Authentication of the users depends on how you do the policy in your domain. We support either daisy chain, so one-by-one domain communication, or the tree model, which is more preferred and more flexible for the reservation on a big scale. And what is important is that implementation independent. So the standard itself is defined as a web service interface. And whatever language, programming language, and whatever tools you have in your domain, you can still adapt the NSI to make it working. So we have implementation in Java, C++, PHP. There is one in Perl, and it's still working together and can set up the global circuits. This is a brief view on the history of the NSI, of the milestones that we had in the NSI. So we started our work in about 2011, 2010, and we standardized the first version of the protocol in August 2011. That was connection service, NSI connection service in version 1. We had followed that by several demonstrations at the future internet events, supercomputing, etc., trying to validate the protocol in a real environment. The tests were performed mostly in the Glyph network, so in the quite big and the global scale network. And we defined the features that are required for version 2. And the version 2 is about to be released in a couple of weeks, probably from now. We have a session tomorrow working, finalizing the standard of the version 2 of the protocol. And the main thing that is added to that are the surrounding services, which are required to service to operate in the real operating environment. So this is monitoring, for example, topology exchange, topology discovery, and stuff like that, also authorization of the users. This is how the testbed of the NSI looks like at this moment. This was presented at the supercomputing event last year in Salt Lake City. So there's 14 sites. There's actually 15, but I would just hide one because it will be mentioned at the end of this presentation. Those sites are distributed all around the world. So there is Europe, there is Asia. We have sites in Korea and Japan, also in the US. And there is 7 tools that is using the NSI in this testbed. You have mentioned them here. And this is the entrance that are using these tools for, some are using in the testbed, but most of them is using that for operational purposes. So in fact, you can use this environment for setting up the real circuit for the end users. It's still in testing phase, but it's a kind of operational service. So for example, in the Jump Bandwidth on Demand service, we are using the NSI connection service, version 1. The version 2 is going to be deployed as soon as the standard will be available. And it's really operational. You can take a look on that. Going to the Jump web pages, you will find the Bandwidth on Demand service. It's using the NSI. The NSI allows us to go beyond the Jump network. So we can contact, for example, Japanese guys and set up circuit between them. We have a peering with the ESNet. We have a peering with Internet too within that service. So it's really a global service, and this is a kind of a proof of concept for that. Also, the Glyph network is using the NSI. There is an initiative called Automated Goal. The goal is the point when the connections are going in and out, and they are crossing actually them. They are planning to do that dynamically. And the NSI is a protocol that was selected for doing that. So they have the NMS, what they do is do most of the stuff manually, and what they want to do is to deploy the NSI on top of that to allow users to configure the circuit dynamically. This is the sites that are mostly interested in using the NSI. I mentioned Glyph already. There is also the Network for Large Hadron Collider. They're also very interested and also active on the NSI group. There's the people from the Nexpress project. I had a demonstration for the last 3 days on using the NSI for the Nexpress project. I hope some of you has seen it. We are setting up a circuit from Poland to Amsterdam in a couple of seconds. And actually, this service was using several times as a production service because the static connection for the radio oscilloscope was down, and they decided at the last moment to use the dynamic circuit provisioned through the NSI and Bandwidth on Demand services. And that was kind of a risk because those services were in test phase, but they worked perfectly, so they can did the observation, and they were very happy about it. So now I'll go to the main part of the presentation. So about the space, Juno Space SDK, and how we deploy the NSI engine in that environment. So starting from the problem, you have a Juniper domain. You have several boxes, whatever kind of. This is the MX. That's 240, I guess, hertz. And you can configure them in several ways. It's free of you how you're going to manage your domain. So you can use the netconf, sending the XML remote commands to configure. You can insert the configuration, upload the configuration through the SSH, or just log in and use the CLI for configuring the particular equipment. You can also have the network management system that is a kind of automatization or make some things simpler for you for a configuration. Everything is fine unless you go into the large scale. So it's easy to configure 1, 2, or 3 Juniper routers or switches. You can just log in and it give you a minute or 2 minutes for each. So in 10 minutes you can configure your network. The problem is when you have hundreds of that devices. Well, that's something you don't want to do. So either to the netconf or SSH, it's a quite of problematic thing. So what you really need is a network management system who has the big picture of the network and can help you with that because he knows what is going on in the network and he controls the resources that are there. So you might have problem with seeing all the hundreds of the devices. The NMS will not and will aim you to reach your, to help you to configure the network and deliver the services. But what if you have a neighbor domain and you want to do the services with them? Usually you can do that manually, so you can call a guy on the other side and say, I will terminate my circuit at this port. You need to configure that on your side and deliver the circuit to the end user. The problem is, I will use the live example. One of the guys in the PSNC wants to send a large video file from Poznań in Poland to Chicago in US. They call us and say, I need a circuit, a 1 gig circuit, for 1 or 2 days to have a fast pipe to send this file. So I called the guys from Glyph. It takes a while because there was some conference, people were busy. The mail was in the inbox waiting for being read. It takes actually 3 or 4 days to get a reaction on that email, and probably in the next 2 days the circuit will be there. But the guy from the video file called me and he said, I already sent it through the regular IP network for the 3 days. So that is why you need to do that thing dynamically. So you need to have a way that the user on the any side of this circuit can have dynamic provisioning. So I need a circuit, give me that circuit. He can use the NSI between the domains, as I said at the beginning of the presentation, to have the circuit going through all the domains along the path and can configure that in a couple of seconds. Then the service is reasonable, so he doesn't need to send his file to the IP network for 3 days. He can really do that in a couple of hours, actually. Another thing is the complexity of the network management system. As you probably know, those things can be really complex stuff, have a lot of modules. Some are included by default, for the others you need to pay. Not all of stuff is what you really need in the NMS. If you want something really simple, just to creating a connection services, for example, you need, of course, monitoring and stuff like that. But still, you need to install a very large machine dedicated for the NMS. And there's a lot of features you will never use, actually, in the network. In addition to that, you have also the external applications, so stuff that you do for yourself, for your network, as the administrator, like accounting system or external monitoring, statistic gathering, whatever, that is interact with the NMS and also with the boxes itself. And that's the main problem, because if you change the configuration here, the NMS may be not aware of that, or he need to check the states. And you have several states of the network in different places, which may be not the same as the real network condition at this moment. And that's the problem. So what we proposed here is to get rid of the complex NMS. Instead of that, just use a simple NSI agent with some logic behind it, and use the Junospace SDK, which is simplifying things for the management of the Junos hardware. So the Junospace SDK is not a network management system. It's the environment that allows you to perform some operation over the network, but it gives you an interface and an easy way to do that. So whatever you want to do with your network, you just need to define it configuring the space SDK and you just have it. And Juno Space is giving you the opportunity to have all the states of the network in one place, because he knows he talks directly to the network and it's on the place. So we have, for example, except the NSI, the other application that is interacting with the network, it still talks to the Juno Space. So the Juno Space still keeps the consistent state of the network and the hardware that is below. So how looks the application in Juno Space environment? It usually has three main components. The business logic, which is in our case, this is the NSI agent, and logic that we need to provide the services. And then we have the REST API, which is contacting with Juno Space environment on the one hand, and also with other applications that are deployed in the Juno Space environment. And it has a simple web service website for configuring and requesting the circuit. This is something we actually are not using. You need to define it for some purpose, but you don't need to use it actually, because for in our case, we are using the NSI protocol from the external client, so it's connecting directly to the application, not through the web page. What we have here is the main components that we are using from the Juniper Space SDK. We have a service device discovery model, which is in fact responsible for topology gathering and keeping the state of the topology consistent with the real network. We have a signaling box that is responsible for putting a configuration into the network. This thing is quite complex. You can configure your Juniper boxes in several ways. It's up to you which way you want to do that. And the user management is the box that is responsible for authentication and authorization of the end users. So the process is that you create a reservation here in the web interface, in the GUI. This GUI or server is sending the NSI request to our NSA agents. And NSI agents is talking with all those three modules to deliver the circuit to the end users. And then, of course, you have a call box. So in case anything goes wrong with the network, you have some issues, you are, for example, a topology was changed and there's an alert that the link goes down or whatever, you can have back information to the NSI application so it's aware of the things that is going on in the network. So it's a feedback system. You can configure the network. But on the other hand, you can get information of what's going on in that. This is the overview of the components or modules that were implemented for that purpose in our application. So message delivery layer is a part of the NSI standard. It's just a layer that assures you that the message was delivered or you know it was not delivered. The state machine is a quite complex thing. It's the main logic actually, because it decides what to do with the reservation at this moment, based on how did you process it, what messages were received from your neighbors, etc. The resource coordinator is the module that is really configuring the resources. At this moment, we are using Juno scripts to configure the Juniper boxes, and with proper attributes, we set up a VLANs or MPLS path depending on our needs in the network. There is a topology service which is getting the topology out of the Juniper boxes, so we know how to configure the circuit locally. Log service is just for debugging purposes. There's of course the user interface and administrator interface as a GUI, so the feedback to the end users, to the administrator on what's going on in the system and how to reserve a circuit. And we use the SSL REST API to communicate with the SDK, and all the job is actually done here. So Juniper Space SDK just simplify the things. You can do most of those manually, but it does not scale. The Juno Space just give you the tools that allows you to facilitate you with the management of the large-scale infrastructure, if it's still based on Juniper, of course. So if you go in the different vendors, then this will not work. So simplifying things for our application is that it has very few main functionalities. You have the NSI interface at the top, so you can talk with the other domains. You need to know what is in the network, so you need to know the topology and the details of the internal domains. You need to keep the state of the NSI state machine, so how to deal with the neighbors for the reservation, and of course the resource controller who is configuring the network. The orange components are related to the NSI protocol. So this is the NSI standard, those two, and they are responsible for inter-domain reservation at the global scale, so talking with your neighbors. The blue components is responsible for the local resource configuration, so putting up the circuits locally alive. And of course, at the very bottom, you have the Juno space, which is doing all the dirty work you don't want to deal with. So as I said, what it's give you the application that we develop you. If you have a Juniper-based environment, whatever kind of, you have router switches, whatever you have there, if you have a Juniper boxes, there is 99% chance that it's working with a Juno space because only old hardware is not working. It's based on the operating system that has implemented the protocol. So if you have new operating system, the Junos on the boxes, it will work with Juno space SDK. You just need to deploy that. And it's very easy to deploy this part because you just take it, for example, from the Juniper store, the space application store, and this is plug and play. You just install it, and you need to have a very little amount of configuration to put that things alive because all of the dirty work, as I said, is done here. So all the topology discovery are automated. You don't need to configure a lot of things. You just need to do some policy stuff here, and you need to configure how you're gonna deal with your neighbors and how to find it. But these things are actually standardized in the NSI protocol, so it's not a big deal.
Radek,
yes.
I'm sorry, but
last two slides.
Yeah, okay.
Yeah, this is last two
because
slides.
we don't have even time for
questions. Sure. So we tried to follow the NSI version 2 standard as it was developing. So we are almost there. The standard was changing and evaluating all the time. Now we have almost stable version. So as soon as the standard will be released, we will just update our software and we'll be fully compliant with the version 2 of the NSI. We communicate with using the REST protocol, and the NSI is a separate entity. So it's an application within the Juno space environment. It can collaborate with other applications in Juno space if needed, and it's still independent from the network state because Juno space is keeping a hand on that issue. We discovered we were using the EX series switches in our testbed. We just confirmed it working with the MX as well, but we didn't build a testbed to confirm that in a large scale. So we just working on the EX boxes. We're using the device management API, and for the configuration, we were using the script management API. So the scripts, the Juno scripts were on the boxes itself. We're just sending the configuration attributes to set up the circuit, the MPLS path or the VLAN as needed. And we developed a simple GUI for requesting the circuit in that domain. What we need to do is we need to work on a topology discovery service. This is something that is quite difficult if you don't have a particular model for Juno space. We have agreement with Juniper that we get this model very soon, so in a couple of months we probably will be able to support the quite large topologies. And also we need to develop more advanced GUI for to be more friendly with the end users. And back to the topology for supercomputing demonstration, the 15 sites was the Juno space domain. This was actually our testbed, which was attached to the Pioneer regular node in the Glyph testbed for the NSI. And we were operating the same priority as all the other domains, so we can also request the circuit to our domain, and it works really fine. So we have a proof of concept that the tool, the application that we developed is really working and is compliant to the standard that was used at the supercomputing demo at least. Okay, thank you very much.
Thank you, Radek. I'm sorry we don't have time for questions now. Maybe at the end there will be time for questions. You can proceed. So next up is Warren Matthews for the presentation of the Pythia tool. Yeah, you can take this microphone.
Good morning, everyone. I am Warren Matthews from Georgia Tech. Before I get started, has anybody actually heard of our project? Is anybody actually here because they can't wait to hear more? Okay, good, that's fine. Let's see. So Pythia is a tool we've developed. My background, actually, maybe I should back up a little bit. My background is particle physics. I got involved in networking because I was one of those guys that needed to shovel data around the world, and we didn't have enough computing infrastructure of our own to reprocess our own data, so we needed to move it around. And back in those days, the network people weren't very helpful in telling us where the problems were, so we had to kind of figure it out for ourselves. And in a way, I've kind of carried on the same theme. I'd love to automate myself out of a job, and have the computers all, tell us where all the problems are and send off the emails. And Pythia in a way is kind of an extension of that. I know from my own experience that, we like to see the raw packet times and lost data. But Pythia is for those who want to kind of jump the queue a little bit and get some more information. So what we've attempted to do is detect, diagnose and localize network performance problems. Now, the algorithms themselves should work on a wide range of data, but our implementation is using OAMP data from perf sonar hosts. It certainly could work on bandwidth measurements and things like that, but it doesn't use things like NetFlow or SNMP to gather data. We don't rely on anything from the network other than the end-to-end measurements to figure out what's going on. And I also think that if we wait for a customer to actually complain about something, then we've already kind of lost, because we need to, we want to stay one step ahead of them. But anyway, so our goals really were to try and troubleshoot problems in near real time. We want some quick answers. We also want to use the information to help plan upgrades and changes. We're specifically looking at short-term events, things that come and go. Before, as you pick up the phone to tell somebody there's a problem, by the time they actually look, the problem's kind of gone away, and they say, nothing wrong here. You're imagining it. But we also think that major outages are quite easy. If there's a major network outage, you don't need sophisticated tools to tell you what's going on. But what we also set out to do was make it scalable and certainly configurable. Different people have different needs, so we want people to actually have the ability to tweak the algorithms fairly easily. And of course, we want to be able to visualize the summaries. So the design is nothing particularly revolutionary. The key here, though, is the lightweight agents. This is running on perf sonar boxes, which are doing measurements which are out there being used by people. So we don't want our addition to cause problems and to get false positives. So it's very important that the agent sitting on the perf sonar box is very lightweight. And then they look at things like in our case, one-way delay, loss, and reordering. And then the algorithms process that information using the definitions that we provide as default, plus anything else that the operators may want to add, and that gets output into some visualization. So I'll take a moment here. This map is supposed to show this is the US state of Georgia. Atlanta is up here. The school districts, what America calls K-12, K through 12 school districts, are typically broken down on county boundaries. These small parts here, these are the counties within Georgia. And the green show where I've actually got a monitoring device. The perf sonar boxes are hosted by the school district. And on 14 of them, we've installed Pythia. The only reason that we don't have Pythia on all of the boxes is because some people are doing port forwarding, which is not desirable and kind of messes up some of the measurements. But we've got quite a wide test bed, but I want to be clear, this is not just a test bed. I mean, this is a working network measurement infrastructure that we're taking advantage of to test Pythia. It's not just something that we put together just for our own measurements. In addition to that test bed, we've got a couple of machines running in test nodes within the ESNet network in America. And as soon as perf sonar 3.3 is released, I expect to roll that out to production perf sonar boxes in ESNet. I'm also talking with some of the Internet 2 people about deploying perf sonar then again, and I expect to roll that out after 3.3 is released. But we're also talking about the possibility of putting Pythia on 9 US Atlas Tier 2 sites. There's an awful lot more US Atlas sites than that, but right now Pythia doesn't scale too well. I'll kind of touch on that again in a little while, but we don't have the ability to look at hundreds of data sets. So get back to the point. So when we're talking about detecting a network problem, what we're trying to do is, first of all, set a baseline and then look from deviations from that baseline. So you can see a good example here. This is real data, it's not something I've just made up, but by baseline what I'm talking about is the normal working well kind of performance where you've got a typical round trip time. In this case I think it's about 11 milliseconds between from one persona box to another one-way delay I should say. And then at some point it just goes a little crazy and you get hundreds of milliseconds one-way delay between those hosts. And this lasts, I think that's about 5 seconds. So you can see, this is something that would probably cause a problem to some of your applications, but it's going to be really hard to actually figure out what was going on there. And so that's where Pythia comes in. What we do is we kind of remake this graph and we look at the baseline and then we look at the deviation. And so what we look for is instances where we've got a peak and then we've got a second peak. And if we see that second peak, or specifically, we look for where it turns back up again. We stop processing. Once we know it's turning back up again, we stop looking, because that's going to be just a waste of processing power. We know that it's turning back up, so we consider that to be detection of a problem. And then once a problem's detected, the Pythia algorithms look to the signature of that symptom. What I mean by that is we've got a whole bunch of examples coded into the program where you've got a certain combination of events, certain losses or reordering or a certain amount of a signature of the changes and of delays. And that's how we try and assign a diagnosis to that. So what we've got is some congestion types, routing events, various loss events. We don't see a lot of reordering, but we do see a lot of end host effects. I might touch on that later, but I think it is worth noting that with Gammon especially, we've taken a lot of old servers that have served their purpose in a cluster and are about to be thrown on the trash heap, and I kind of got in there and grabbed them before they've been thrown away. So one of the concerns is we're going to get a lot of end host events because these old machines are, we're about to be retired and they're not up to the job. But I'm actually finding that some of these older machines are perfectly capable of, they've still got plenty of life in them for this kind of project. So the end host events don't seem to be necessarily hardware related. I'm not making problems for myself just because I'm using old hardware. So I know I wasn't particularly eloquent just then trying to talk about how we do the diagnosis, but maybe this gives you a bit better of an idea. This might be a little blurry, but I think you can get the idea. So we have the input, the one-way delays, any loss or reordering data. And the first thing we do is look for things called context switching and end host noise. So we throw out anything that we consider to be, or has symptoms, signature that could be an end host effect. But then the next question is, are there changes in the delay? That graph that I showed before, where we see the sudden change in the delays. And then a series of yes or no questions. So we look for things like clock changes in NTP, if there's pure lossage, pure loss, maybe a short outage, if there's things configured like large buffers, if we see any reordering. And so we have this chart. And again, to really sort of maximize the processing power, once we go down one side, we do not consider the other side. So it is possible to diagnose several things, but we want to get to a quick decision. We certainly only want to go through the data once, because like I say, we want to do this in near real time. So these are some examples of things we've actually seen on the network. And the important, there's a missing graph. Interesting. So engineers know what congestion looks like. I mean, probably you guys can sit there and look at a graph and just the one-way delays and losses and that, but none of us have time to sit and sift through, potentially hundreds of graphs on the off chance that there might be a little congestion in one of them. So, Pythia is going to help you spot this quicker. Typical things like, the link is overloaded, or there's a delay correlated with loss, or even if there's some random losses. So we have these signatures. Obviously, these are selected to show you clearly what's going on, but sometimes it's a bit fuzzier. But there is a difference between an overload and a random loss. The pattern of the one-way delay is certainly very different. Oh, so they're the extra graphs. There you go, animation for you. But the point remains. These large triangles, so-called large triangles. Suddenly, there's a massive increase in the one-way delay. So I'm going to spend a little more time on localization than I did on diagnosis, because this is an important point. I gave a talk similar to this in America to some people from the ESNet network. And I kind of wanted to skip over some of the under the hood stuff, because I wanted to get the point with, is this interesting to you? Same kind of question I'm asking here. I want to know, is this useful for your network? What would we need to change? But the people there were very interested in what's under the hood. And with the localization, it's not quite so simple. So excuse me if I labour the point a little bit. But the point is, we use a thing called network tomography to localize these anomalies. But the important point is Pythia is not able to localize individual events. We're looking for the most likely cause, the most likely location of a problem. So we're using a thing called range tomography. This very simple example here. So the S's are the hosts on the end, and the squares are the routers in between. I'm not a computer scientist. As I said, my background is physics, and I got into networking because I had to move data. So you guys might be more familiar with some of these approaches than I am, because my troubleshooting approach is pretty much the binary. I don't necessarily believe in coincidences. If suddenly, something's gone wrong, I'll make the assumption that it's one particular place that's gone wrong. It's not suddenly half my network is having problems. But there's an approach called analog tomography, where you look at the actual measurements, you look at the variation in the round trip times or the one-way delays. So you have this continuous, basically random variable. And of course that's sensitive to noise. Even a perfectly quiescent network is going to have some variation. So you have to measure things for a long time. And with Pythia, we don't feel we have that luxury. Another approach, my typical approach, is just a binary tomography. The link is either good or bad. And if I find one part of the network which I can happily consider bad, that will be where I focus my troubleshooting points on. And again, it's a limited resolution. So given the example of the Boolean tomography again, so again, perhaps I might think it's a bit unlikely, but say, 4 links on my network suddenly all go bad at the same time, and I'm measuring these losses, the examples I've given here, so I'm measuring 15% loss between router 1 and 5, 5% between router 2 and 5, and then 7% between 3 and 5. Well, Boolean tomography would tell me that the problem is between 4 and 5, because that's the only common hop where I'm seeing all these problems. And again, Occam's razor kind of thing, I would suggest, that's where I'd be focusing my time. But it's not impossible that that's not where the problem is. So range tomography attempts to do the best of both worlds. It looks at the possibilities. So I've got those measurements that I mentioned before, and what I can actually do is I can associate a probability. I did work these out before, but I'm not going to go into the details, but the probability of the problem being between 1 and 4 is 10%, between 8 and 10%. The probability of the problem between 4 and 5, which is where I would think it was just from pure Boolean tomography, is actually only 5%. So there's probabilities of where the problem might be, and range tomography allows me to be a bit more accurate, a little bit more, considerate of the possibilities. So all that with being said, just a review, I went over the goals and the architecture before, but Pythia then pulls all this data together, the one-way delays, the trace route, all the data that the perf sonar boxes do anyway, brings them all in and does some pre-processing, runs the detection. As I said before, the localization and the diagnosis is actually done separately, and then we have the visualization at the end. Currently the visualization is more of a kind of a maintenance thing. So, we just track the number of events we see each day, the breakdown of what those events are, other histograms and pie charts breaking down the nature of the diagnosis. But what we're really interested in as the people that operate the network is answers that are going to help us troubleshoot quicker, or even indications of where our network needs to be improved. So what we've been trying to do is come up with new ways of visualizing things. So here the data from February, which just happens to be when I was writing the paper for this conference. Across our Gammon testbed, there's 1,380,000 and some thousand events. Of those, 54% were immediately thrown out as being just end host noise. But as I say, it doesn't actually seem to be related to the hardware itself. We've got 16% delay correlated loss, and 8% random loss, and 7% were actually undiagnosed by our algorithms. But the point here, in Georgia, the schools aren't on a research network. The research network that provides connectivity for the universities does not extend into high schools or middle schools or elementary schools for that matter. So some districts get it. Some districts have good network connectivity, have good network people operating them and do very well. Others don't. Many of the districts in Georgia, many of the districts that we have Gammon sites are very congested. They're, to all intents and purposes, useless for any interactive application during the day. So when you see these large numbers, 16,000 events between Georgia Tech and Rayburn County schools, almost 12,000 events between Jasper County schools and Sumter County schools. That's a lot more than I would expect to see in a typical research network. But we know that those districts are highly congested. We know what the problems are. We're not really discovering anything too controversial. But in this, eventually I'll color code this front end, but we have the ability to filter out certain events. In this particular example, I'm not considering the end host effects or the unknown events. These are just what we consider routing events just for this last month. So a lot of events. And similarly, again, probably eventually color code this table, but it allows me to break down for a particular route. This happens to be from Georgia Tech to Putnam County schools. We look at the breakdown, and for this particular time slice, there were 64 events that were classified, diagnosed as random loss, 11 that were considered delay correlated loss. And we can break those down different time slices and see how things vary. Because if I wasn't quite clear, what I'm very interested in fact, one of the things we were criticised for is the sensitivity, those thousands and thousands of events. But I like that. As we're trying to make school networks more like research networks, we're interested in these subtle effects. We're interested in these things that are going to throw off the highly interactive applications, but maybe not even be noticed long term. So having the ability to see these brief events allows us to push forward to that, 5 nines kind of network performance. Oh, okay, oops, okay. All right, well, quickly then. So this is just the visualization for the localization. The brighter red dot means there's a higher probability that that's the location of the problem. But like I said, there's two separate algorithms, and the one doesn't necessarily give rise, just because you've localized an issue doesn't mean you actually have a diagnosis for it and vice versa. So we're interested in, we're looking at probabilities, and again, these are three examples of congested districts, so it's not surprising that, they're dominated by congestion bursty diagnoses. And there's some links to some papers. Are there any questions?
We will not have time for right now
Okay.
questions, but I'm trying to,
Very good.
Again, I need to apologize to the speakers, but understandably, all the presentations are very are packed, very interesting stuff, but we don't really have much time for enough time for them. So next up is Ivo for a second Juno Space related presentation about using Juno Space to detect what?
To monitor video streamings in the network. And not only Juno Space, but also Juno's SDK
Utilize
on
yes.
routers.
Yes.
Our application called Monstream. It's designed to monitor our 3D video streamings from PSNC suite. So what is 4K? I think you know it. 4K, it's a bigger image, it's a better quality. It's 4 times more pixels than in Full HD. And now 8K is approaching, and 8K is 16 times pixel and data as Full HD video. So, for example, if we have 4K 3D image, it's 500 megabits if it's compressed, or even 12 gigabits if it's uncompressed. So these streamings have very high demands on the network. At PSNC, we are working on 4K 3D node. We are developing. We have this node with very interesting capabilities. We have hardware. We are doing our own hardware. We are also working on our own software and video streaming client server application from PSNC. It's using JPEG 2000. It's using RTP streams encapsulated in UDP, what's important for this application. And what is also very interesting that 3D streams are transmitted through two independent two independent UDP streams for different ports. So every 3D transmission is real two streamings that are connected together, and both have to be good quality. Some use cases of video streamings are need higher quality than, for example, watching a movie in your home. We are working on live streamings for theaters, from content servers, from live events, and in such cases, we need very high quality of image. A second important use case for us is interaction through streamings. For example, you can try here at Tirana to control a robotic arm that is in Poznań, 2,000 kilometers away, and you know that delay is a crucial parameter in such use case. Both use cases were motivation for us to prepare some application that will be possible to measure network performance. Existing solution provide us only end-to-end monitoring, which is what is not sufficient to localize a source of disruption and to resolve it, because if we can only know that something goes wrong, we don't know what and where. So this is our main motivation for this one, and keep in mind this motivation, we write it target features of our applications. So Monstream is capable to monitoring IPv4 and IPv6 streamings, unicast and multicast. We are measuring parameters of any RTP stream, not only PSNC 3D streams, because we are not parsing compressed video data. We are only working on RTP headers. So it's a universal solution. Important feature is centralized stream management for network. So we are using Juno Space here to provide one point for user and for streaming applications to configure streams and to read collected information. Visual presentation of collected data, of course. API for streaming monitoring for streaming application, because if you want to monitor streams, we had to know which packets are streams, and nobody will put it by hand. And of course, no impact on transmitted data. You know why. One of key things on such application are monitored parameters. There's no much standardization in this area, especially for video and especially for two streaming transmission that contains two streams. Packet loss is important, especially with JPEG 2000, because this codec was not created for network transmissions. And if we lose one or two packets from image frame, it can be impossible to decode entire frame. So losses, for example, 1% on the link can make the transmission impossible to watch on the client side. Stream jitter, we are now using stream jitter defined with RFC 3550 that define RTP protocol, but also this jitter is not designed for bursted traffic like video stream, because each image frame is sent in one moment in the time, and it contains many packets, of course. So it's not it's a CBR, but it's very bursty from the network point of view. So we are also created our own jitter that is taking into account not every packet in the frame, but only a first packet in the frame, which we believe behave better, and we are investigating this, of course, with our test streamings. Stream synchronization and interstream jitter. As I said, our application uses two streams for 3D streaming. So not only jitter inside one stream, but also a jitter between both streams are important, and synchronization between these two streams, because in 3D video, the synchronization of image for both eyes is more important than synchronization of video and audio in standard streamings. So we have to create some metrics for this. In relation to use cases that I mentioned, packet loss, of course, is directly responsible for image quality, and jitter and stream synchronization are directly responsible for delay, because to compress jitter errors and stream synchronization, you need bigger buffers. If you have bigger jitter, you need bigger buffer, and bigger buffer introduce additional delay. And in robotic arms use case, for example, it's 20 milliseconds of delay from Poznań to here, and each millisecond is important. About architecture of our solution, we have mostly probes on every router on the network. They are running on MSDPC cards that are used to do deep packet inspection and to calculate metrics. And there is one monostream manager that is a central point of management for entire network, with REST API for streaming application and web GUI for user. Streaming application, when streaming application that is using our MonStream, when new stream starts, streaming application configures parameters of the stream, IP addresses, UDP ports, and this information are configured on each router on the network, because streaming application don't know topology, don't know routes inside the network. We are looking for the stream on each device, and results are gathered back by manager, and MonStream manager visualized this path inside the network, and are looking for problems. Now, on the beginning, these are only triggers to find where parameters got worse, and to raise alarms if it's desired. MonStream Pro, as I said, installed on MSDPC card and are responsible for providing data. We are using Junos SDK for this part of our application. Each packet in the streams are some duplicated inside packet forwarding engine of Juniper router. Copies are sent to MSDPC card and are measured here by one component, and measurement results are provided up to routing engine to second part of MonStream probe, and of course you can check this results by CLI, but they are also sent back to Junos space where they are gathered from entire network. So this solution is not affecting traffic. MSDPC card have its own operation system, so also some problems with, for example, throughput or other are not affecting device, so it's safe for your network and for our network, of course. MonStream Manager is a central part. It's installed on Junos Space appliance as one of applications. It provides you visualization of the flow, web GUI from administrator, REST API, and it's of course collecting data from probes. Here we have a prototype type of our UE that you will be possible to see it in action on our booth after presentation. The path is visualized. When you are logging, you have to choose the stream you want to monitor. Stream is visualized. You can choose one router and to see what are the parameters that are monitored on this router. Of course, some charts. What we plan for future? We plan to release this application as an end product for supercomputing conference in November. Will be available in Juniper Application Gallery, so everyone will be have possibility to access it. And we also plan a common demonstration with our media group with human-robot interaction on next events like Terena. Not entire traffic is transmitted using IP in this demonstration, but some image will be possible to be monitored by our application, and you will be probably possible to see it in real condition. This is our internal project. It's 5 people in team. And after presentation, if you, I don't know if we will have time for questions, but
yeah, there's a demo in the break.
Yes, there is demo in the break on booth 14.
Okay.
So if you will have more questions, I will be waiting for you.
Perfect.
On our booth.
We will have
So
time for questions also. Yeah. Thank you very much. We didn't do this for the rest of the speakers, but we're running. Okay, and the last presentation is by Xavier for the integrated NMS of Giant.
Right.
Again, I think Juniper related.
Sort of, yeah. Okay.
Okay, we will have, I think we will have time at the end for questions for all speakers. So please do note what you want to ask them. It's a bit different from what we usually do, but we're just running to make sure that everyone has time for the presentations.
All right. So I'm the last one. I know that I am between you and the very needed coffee this morning, so I try to keep it short. I will be in the Dante booth afterwards as well, so if you have any question or anything, don't hesitate to come through the booth and ask me anything. So I'm Xavier, work for Dante. I'm the IP manager there. And this morning I will go through what we've done in the last few months and the last actually 10 months on the tools and where it's coming from, what tools we're using, and what kind of changes we've done in the backbone and on the tools to match that up. So starting with a bit of background, in 2011, as you may know, we started a procurement to replace our DWDM and TDM switches. It used to be provided by Alcatel, and we wanted a new platform to support 100 gig and to be also more flexible with new technologies. At the end of this process, two vendors were selected. We chose Juniper MX platform for the IP MPLS and Infinera for the DWM platform. And this obviously meant new changes in the platform, the tools, but it also meant a new way to do the network, a new way to offer services. And that is really shown on the approach that we've took to offer services. So in the past, we had a very three-tiered approach where DWDM at the bottom, we had layer 2 services offered over SDH, and finally IP services on top. But as you can see, we had some differences, and especially here, IP MPLS only, we couldn't offer the layer 2 services. So services like Gen Plus didn't reach everybody in the network. So one of the major changes that we put in the network, on top of obviously replacing the underlying layer, is to merge and converge the layer 2 and the IP layer into one IP MPLS platform where we could have all the services reaching actually everybody in the network. So that is a very good change, and it's also a change that is impacted on the way we approach the tools as well. So Gen Plus is the Gen's layer 2 service where we can offer point-to-point on services. And as I was saying, in the past, we had this coverage, and that is about 75% of the network. So that means we left out 25% of the POPs couldn't reach or couldn't join the point-to-point services. With the new installation and after the migration, we're now reaching all the countries. All the POPs are actually on the Gen Plus cloud. So this means that now we have 100% coverage of layer 2 and Gen Plus services. This means as well that actually we're now bringing 100% coverage for services like bandwidth on demand. You heard about bandwidth on demand and how to implement it. And now on Gen Plus, anybody can have access to those kind of services. That's good, but what does it mean in terms of tools? Because I mean, we're here to talk about tools. So this is quite a change, quite a new way of improving things. And let me start with showing you what we had in the past and go through the list of tools that we're mainly using, the tools that are helping us maintain the network, and the tools that we are relying on. So first, we have 5 main tools that are either developed in-house or are ready services or ready tools. First, we have the configuration management. Configuration management, we call it the OpsDB. It's a homegrown database based on MySQL. We have the monitoring side of things. It's based on Cacti and the dashboard. We have the reporting side. Obviously, we need to be able to make sure that we report on our performance. and we have the service provisioning, bandwidth and demand. Following the migration, we introduced a couple of new tools, Genospace, we heard quite a bit about it today, DNA, so Digital Network Administrator from Infinera, and recently we are...
What is network activate? Is it a Genospace related thing?
Yes, yeah, I'll come onto that a bit more. It's basically something that we're using for the provisioning. And yeah, so for recently we introduced a capacity planning tool called OpNet that is helping us for the capacity management and fault analysis. Right, so let me talk a bit about Ops Database. So the Ops Database is basically one of the core tools that we're using. It is a tool that basically knows everything about everything in the network. Every pieces of cable, cards, optics, plug-in, circuit, everything is recorded in this tool. So this is where all the information is documented, stored, and as you will see in a moment as well, how all those tools are connected to each other. Then we have the dashboard. So the dashboard is as well a tool that was developed in-house. It's the monitoring tool, so the main tool for our NOC to be able to see alarms and have information about the status of the different circuits and different links and services in the network. It's basically making the link between the different layers in the network because it's listening to SNMP trap coming from the Juniper equipments. It's also listening, and bear in mind that we're still like 10 months ago. So at the time, it was listening as well to the Alcatel equipment linked to the Alcatel NMS. So we had those two links. So we were receiving alarms from both the Alcatel NMS, from the Juniper equipment. And you can imagine that in case of a fiber cut, if you're listening to all the equipments and you just putting the alarms on the dashboard or in any presentation tools, you will have dozens of alarms for a single event. So what we've done and try to make sure it was simplifying all that. So we linked the dashboard to the database and created some rules within the dashboard so it can link all the events together regardless of the platform, and then create an aggregated alarm saying, okay, I have an alarm between those two ports in the network. And then we map it up with the database so we can actually make meaning of it. So then instead of saying port X123 on router B is down, we can say, actually, we have a possible fiber cut between Paris and Geneva, for example. And this is the kind of information we're trying to get from the dashboard. Then we have Cacti. Cacti is a readily available tool we're using for graphing purposes, so traffic analysis and making sure that we have some data about the different circuits. We did some tweaking on it, so it's not straight out of the box implemented. We have high availability, so actually we have two nodes of Cacti that are redundant, and they're automatically backupping each other. So that's just for the availability side of things and making sure that everything is redundant. And we have then the monthly service report. Monthly service report is our reporting tool, the tool that's the report that we make available to all our NRENs. On this tool, you can see our SLAs, so how well we're performing on the circuits. You can see availability. You can see the list of circuits. You can see traffic values. So everything is aggregated and put in this tool. But to do this level of aggregation, you can imagine that the tools need to talk to pretty much every other tool that I talked about earlier. So you have a link to the dashboard, you have a link to the database, you have a link to Cacti, and everything is then collated, put together, mashed up, and presented in a nice way, where you can have also historical information and so on. And finally, we add the bandwidth and demand. So it's a picture of the portal, where that's where you go when you want to make a request, and it's talking. So at the time, it was talking directly to our SDH box. So we had a link to our Alcatel NMS, which was then configuring circuit in the network. So if I put all that together, on a map, this is basically the tool infrastructure that we had. So you have the database in the middle and links on the different tools.
SD is what?
Sorry?
SD.
Oh, so yeah, SD, it's our ticketing system.
Okay.
I didn't mention that. It's we don't have full control over it. It's basically the tool that the ticket system that used by our outsourced level 1. So there is a link so we can export data from the ops database to SD for inventory information and those kind of things, but it's not a tool that we can easily retweak. So, based on this infrastructure, sorry, I wanted to overlay basically the relationship within the tool and where the communication flow, in which direction the communication was going. And I guess you can already say, but there is a problem there. I said that the ops database is the main tool, but all the arrows are actually going out of the ops database. So how do you actually maintain it? And this is done by an operator going there and putting the data manually. So obviously, you're going to tell me there is a problem there. Yes, in this model, the ops database is king. It controls everything. But everything is entered manually, so it's prone to errors, and an error in the core system is then propagated everywhere. So we had to think about it again. So we used the opportunity of the new tender and the change of tools to think about, okay, what are the new tools that this tender is actually bringing us? What are the new things that we will be able to do? What are the new technologies out there that we can use to make things better? The first one was Genospace. So I won't go in detail on Genospace, probably be bored by now about all the stuff that we heard about Genospace. But I just want to mention two things. First one, Genospace is actually the tool that can provision circuits. And the provisioning of circuits through Genospace is done via a module called Network Activate. And what is pretty cool with this module is that you have an API, so you can actually control this part of Genospace via other tools. So we don't need necessarily to go through the GUI. You can do through third-party tools, and I'll come back to that in a moment. The other thing that Genospace can do is get inventory information. So everything is stored in Genospace. Genospace knows about each and every card in the network on the Juniper equipment and can export it to other tools. So you have communication out of Genospace to other things. Then the second tool that we have is DNA. So it's the Infinera platform. It works fairly similar to Genospace. It allows you to do configuration. It knows everything about the network. And it has some ways to export data out of it as well. So yet again, you can gather information and you have the opportunity to push configuration to third-party tools and reprocess it however you want. So you probably can see the trend there. And then finally, I mentioned briefly OpNet. It's our tool that we're using for analysis. So we will do analysis, capacity, planning. And this is really key in the new network because everything, as I said, is based on IP MPLS. So all the services, Gen Plus, are on the same layer as the IP network. So we need to make sure that we have a very solid management of this configuration. And we will be implementing and using this tool for that. Right, bandwidth and demand. I wanted to have bandwidth and demand on its own section for two reasons. First of all, because it's interesting on its own, and there's a lot of interaction, and there's a lot of changes with the new platform. And second of all, is because it's probably the best example of integration and the level of integration that we pushed in the network recently. So first of all, I'll just go through a brief summary of what bandwidth and demand is and how it works. So you have the GUI, which is top layer, and then underneath you have the different components that goes in the domains. You have a set of components that are common to everybody, which is basically developed by the project. But you also have a set of components that are network independent because they're actually driving the network is in each domain. So this means that if you're using Juniper, obviously you will use a completely different technology than if you were using Alcatel or Sienna or whatever. So in our model, we're using Juniper, and I'll explain what the different bits are and how it works. So let me drive through a request. I guess that's the easiest way to see how it works and what we do. So the first component is CNIS. CNIS is the topology information. It's gathering. It's basically where you have all the topology information. It's not part of the request, but I wanted to mention it so you have an understanding where the topology information comes from. Right. So if we start from the portal, I want to have my circuit configured. I want to go from A to B in the network. Doesn't really matter. So go to the portal, make my request, press send, and then that's done. I have no idea what's going on. But under the bonnet, this request is then passed to the Autobahn instance. So that's actually processing the demand, looking at it, making sure that the endpoints are valid, making sure that it's working against CNIS, and validating that it's a valid request. When the request is being validated and considered as a good one, it is then pushed to what we call the technology proxy, and that's where we get to the point where it's domain dependent. And this technology proxy is something that has been developed in Dante, and I simplified a bit this first diagram to go through, but the next slide you will see how the technology proxy is actually interacting with all the tools that we have in Gent, and the way it is actually really integrated and trying to automate as much as possible those kind of requests. So the technology proxy is actually doing the translation between the common request onto something that my network can understand and that my tool can actually configure. When the request is then translated in something that Genospace can understand, it's pushed through the Network Activate API and then translated again by Genospace to be pushed onto the network and finally configured and give access to a layer 2 circuit on the Gent backbone. So let me talk a bit more about the technology proxy and what is actually at the back of that, because it's actually pretty cool, I think. The technology proxy is actually interfacing with most of the tools I mentioned today. You have, obviously, Genospace, as you were saying in the previous graph, but it's also talking to Cacti and the ops database and the ticket system in a slightly different way. So if you remember, when I talked about the dashboard, I mentioned the fact that the dashboard was listening to the network and picking information from the ops database to mark and raise meaningful alarms. So I have my request going through the technology proxy. The technology proxy pushes it onto Genospace and configures it in the network. Everything is fine. It then goes onto the ops database and create a new entry in our database. What does it mean? Is that by default, at this stage, the circuit is configured and is actually monitored as well, because if any event happened on this circuit and the backbone, the database knows about it, the dashboard will pick it up and say, oh, actually, I know what that is. It's the Autobahn circuit. And then you will raise meaningful alarms straight away, and our NOC can then follow that circuit really closely as if it was a manual circuit. On top of that, once that's configured, the configuration is as well pushed onto Cacti. So the circuit, if I start again, circuit goes to Genospace, it's pushed onto the network, it's configured on the database, it's monitored, pushed onto Cacti, it's graphed. So automatically, I am able to see what are the traffic usage, what is the traffic usage on this circuit. If there is alarms, I can pick it up. It's configured into to Genospace. So it's basically a fully end-to-end automated circuit creation on the Gent backbone. And finally, you have the ticket system here, because I've been talking for about 3 minutes about that, but I'm in the ideal world where everything works fine. But what if we try to provision the circuit and it's already used, VLAN is already being used, I lost connectivity between the technology proxy and Genospace, who knows? Then the technology proxy has the ability to have a feedback from GenoSpace or a timeout there, says, okay, I have a problem, something is not right, I can't configure the circuit. So what the technology proxy does is interface with a ticket system, and it will raise a ticket saying, I can't create circuit A, B, C, there is an error, or we have a list of alarm messages that exist, and the ticket is automatically raised. So if the NOC receives a call from a customer saying, I'm just trying to create a circuit, I can't, it doesn't work, then they can go look at the ticket system and say, oh yes, we see that we have a problem, there is a ticket raised, and it's being addressed and handled a lot quicker than if it was just, okay, let me try to find the circuit. I have absolutely no recall, so I don't know what circuit is about, and you need to go then trying to go on the network, find out what could have been caused what and where. So this is basically the level of integration that we've reached on the new platform and basically reinvented the way we were provisioning systems based on bandwidth and demand. So that's the way the technology proxy works. So let me conclude this quick presentation with the new topology. So it's the same, basically same tools, but you can see that there's actually a lot more links between all those tools. They're all a lot more integrated. And if we look now at the traffic flow, there is still a lot of communication. There's actually a lot more communication between those tools. So they're all talking to each other. But the main difference is you have tools, or you have information flowing from the network or the tools onto the database. So that means basically we have a way to validate the information. We have a way to automatically populate, potentially, what we want to do. And we have a way to control and clarify what is in there. So that's quite a big change, but it's not the only one. The other thing that was introduced is the use of RESTful APIs. Because back 10 months ago, if we wanted to make a change, let's say, in the dashboard, or in the database, even worse, and we had to make change in all the tools around, because everything was actually statically talking to the tool in the middle. So a quick change here actually means a quick change there, 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 there. So it's not a quick change anymore. It's basically weeks of work to make sure that all the tools are aligned. By introducing RESTful APIs, we can simplify this process quite a lot. So, as a conclusion, we have now limited manual input, and that's where we want to push that further. We introduce RESTful APIs to make sure that we create distinction between the tools and more independence. And we introduce a new paradigm that is basically everywhere in the new tools, and that's where all the major vendors are advertising, is network is king. So all the information, as much as we can, try to come from the place where everything is, and the place that's all the time correct. It's the network. So that's what we're trying to push, and the model we're trying to move towards. Thank you.
Thank you, Xavier. Very interesting. And I think there's a lot of relation to, well, previous presentations.
Yes, yes, indeed.
We can have some interesting questions and discussion at the end. So, would you like to start asking some questions for the previous presentations? Could I start if you're still thinking about it? Okay, first question to Radek. What I didn't really understand is does the NSI-related application that is implemented on top of GenoSpace, does it goes into GenoSpace, so GenoSpace has a broader view, right, of the whole network and the things that are running there. But does the NSI application have a view of this? How does it synchronize with well, there may be other circuits which are not NSI circuits, right? So how does it deal with that?
Okay, so there's two ways of doing that actually. The NSI itself is just a protocol for multi-domain reservations. Okay. So taking the view from the view of the standard of the LGF NSI protocol, we have an internal database for interdomain topology. So this is all the neighbors, all the other NSI agents that are around us that we can exchange information with. And this is stored internally in the application. The other thing is managing local domain. This is something that is out of the NSI standard. This is managing the NMS in a domain. In order to get in interaction with other domains, you need to go to the NSI module. The small module has a knowledge about the network using the Space SDK. So he retrieves information about the network from GenoSpace and can refresh it, or I get an information about the chase from a GenoSpace.
Other questions? I can continue. I have a question for Warren, for Pythia. The only thing I know about, well, you can use a microphone. The only thing I know about actually tomogravity techniques for network measurement are, I think it's the calculation, or actually the probabilistic calculation of traffic matrices, rather than using actual IP traffic data, for example, net flow data, that sort of thing. But I realize that in that case also it's a probabilistic method. You don't get actual absolutely certain results. You just get an estimation of how a traffic matrix looks like, and it's very CPU intensive. You said in your presentation that the method you're using to correlate and analyze the events is something that can be added to a persona, a node, without putting too much stress on it or something like that.
So yeah, I wasn't clear on that. It's actually decoupled. The detection and diagnosis runs on the actual persona box,
right,
and that has to be lightweight. Some of those results are uploaded to a central server, and that's the bit that's not scalable, because right now we're absolutely banging on this database to do the localization, and that's the bit that's holding us back from having a broader deployment.
Okay.
The way we want it to work right now is anybody who deploys it will have to have their own central server,
Right.
because we simply don't have the capacity to do any more.
Okay.
You're
Okay.
right, yeah.
It's clear now.
Thank you.
Questions? Is it a bit too early? Do you prefer that we go to a coffee break and come back for? So okay, I have at least one more question. I was hearing very carefully, so listening very carefully. I see some common pattern in your presentation, Xavier, and Radek's presentation, because at some point you were both, and I know the differences and the operational requirements that are different in these cases, but from the perspective of someone who doesn't know the details, I see some relationship because you're still implementing circuits at the end with some of these tools. I mean, the technology proxy in the one case, and the NSI application at in the other case. Do you think this could be, I mean, since we're talking about REST APIs or something, could this be more generalized? Well, actually, this is more a question for you, Xavier. Could this tool, I mean, is this too carefully tied to the OPS database? Could other entrants that may, for example, have a chance to use GenoSpace in a similar environment, would they have any use for that sort of thing?
So, it's a very wide question, and you can take it very different ways. So, if you look at the way we approach it with a technology proxy, it's actually very modular.
Right.
Because you have different groups of interaction. So obviously, if you look at the bit that talks to the database, you need to have our database for it to make sense. If you want to look at cacti, anybody using cacti can then use that bit. But I think the most interesting part of the setup, and probably coming back to your question about GenoSpace, we're using the standard API. So everything is standard from Juniper, based on the Juniper equipment. So that means anybody using Genospace just need to set up network activate and can reuse what has been done.
Yeah,
and start
I
configuring
understand
circuits.
that, but well, the question is, well, if I put it otherwise, the question is that okay, the session is about next generation, so to speak, network applications,
Yeah.
network integrated and enabled applications. So I guess there is the pattern. One could say that there is a pattern, or there will be a pattern that there is a broader need for such applications, reusable applications. So Genospace only provides the infrastructure for you to use and write your own applications. There could be a pattern that at least some parts of these applications that you are developing, and perhaps you are a pioneer in this space, at least in our European community, could have more use to other NRENs or other use cases, that sort of thing. So if there are any parts of your applications, of your development, that could be reused in other cases. That's the question, actually.
Okay, so you mean can we reuse part of what we've done for the technology?
Yeah. Could you,
proxy
for
to-
example, make it more generic and provide
Yes,
it to...
yeah. Obviously, we're using, as I said, the API from Juniper.
Okay.
It's based on template. So at the moment, we're pushing one template to configure layer 2 circuits. If tomorrow we decide that actually another template for layer 3 VPN is required, you could use the same work and develop the work that has been done for new sets of services, because it's basically a next set of requests that going through the already available API from Juniper.
Okay.
And that is just using the API. Then I guess from you guys, if you then look at the SDK, which is another approach to solving those kinds of problems, you can as well push different set of services.
Yeah.
Just
Yeah.
wanted to add 2 words to that. What we did with the NSI application for the Genospace SDK is we want to create a very lightweight component that if you have a Juniper boxes and Space SDK, this is plug and play application. You just install it and it works, and you have the NSI communication with the other things, so you can put the services into life. The application will be published in the Juniper gallery. This is the name of like a Google.
I heard that your colleague is also doing the same thing.
Also doing that. So it's open to anyone actually. Whoever has the Juniper boxes and wants to deploy them, he can easily get this application. And despite of his environment, whatever NMS he has, this application can work in parallel. Because the Genospace is a kind of container database that is keeping all the information and synchronizing all the stuff. So what you have in Jan is very nice, because what we did is just a part of that. We just take some of your in blocks and put them together as to make it general, to make it lightweight. You have the full process of operational monitoring of that. So this is the next step if you want to take our application, for example, and deploy it. If you really have that operational at the level that Jean or Dante have at this moment, there is a lot of other applications that you need to install and integrate, like the ticketing system, the monitoring stuff, etc. We just provide a very lightweight component for delivering the connection service and open that to the other NSI agents around the world.
All right, I think it's time to wrap it up. Thank you very much. Thank you all to all our speakers, and especially for doing such a great job to trying to squeeze everything in very little time. Again.